Okay. So today I've got like a couple of problems prepared. Probably won't be working through all of them because there's probably not enough time to get through all of them. But we'll try to do a couple of the problems that I have. So the first couple of problems that I have just involve like graphing some trig functions. So I kind of have 4 problems prepared. I'm thinking of maybe just doing 2 of them for now. And maybe if we have some time at the end, I might go back and do like another one or even the other 2. But I've got one problem here for graphing a cosine function. One problem here for graphing a sine function. I also got one for tangent, and I've got one for secant. So I guess like out of those like 4 options, I was wondering if you guys have a choice, like maybe which 2 do you prefer the most? Maybe I can like create a poll real quick. Let me do that. So I'll let you guys kind of vote on which one do you want the most. Okay. So we can look at the graphing a cosine function, graphing a sine function, graphing tangent, or secant. Those are the 4 kind of problems that I have prepared. All right, so just real quick, I'm just like randomly made a poll. So if you guys want to pick which of these 4 problems do you want me to work on, and I'll pick the 2 which are the most popular. So right now it looks like I'll do an example of graphing secant. Maybe secant and tangent is what it looks like. All right, I think that's probably good enough then. So let me go ahead and, all right, let's end the poll. Okay, cool. All right, I guess I'll look at the tangent one first because that was before secant. Okay. Now, if you guys have any questions at any time, go ahead and either post it in the chat or if you like have a mic, you're welcome to like unmute yourself and like ask your question as well like that. Okay. Okay. Okay, so here we got this problem graphing this tangent function. And let's look at maybe just the first couple of parts of the problem. So finding the period, and it's asking us to find the range as well. So to get the period of a tangent function, okay. So here, if you have a tangent function in this form where a, b, c, and d are just some constants, you can get the period of this function. And the formula for the period, it's going to be pi over b, okay? Now,
Sorry,
if you guys,
isn't it 2 pi over b?
yeah, okay. So it is 2 pi over b for the other trig functions. So for instance, if you have sine or cosine,
Oh, wait, that's supposed to be the a10 and then bx plus minus c not plus c for the tangent function, right?
I don't think it matters too much whether you do plus or minus, because like here c could be like a positive or negative.
Oh, okay. Makes sense.
But if you guys will remember, yeah, so sine, cosine, cosecant, and secant, yeah, that's good. They have periods of 2 pi. And that's why in this kind of more general form, the period is 2 pi over b. But yeah, tangent and cotangent had a period of pi, and that's why you do pi divided by b to get the period more generally, okay? So that's kind of slightly tricky, but keep that in mind that for tangent and cotangent, period is going to be pi over b as opposed to the usual 2 pi over b for all the other trig functions, okay? All right, so that means for this problem here, so for this tangent function, then b is equal to 4, okay? So therefore, the period of this function will be equal to pi over 4 then, okay? All right. And then part B was asking for the range of this function. Who can tell me what the range of the tangent function is? Anyone know that?
All real numbers.
Yeah, okay, good. It's all real numbers. So it doesn't matter if you're multiplying the tangent function or adding something to it. Range is still going to be all real numbers. Okay. So I guess in the interval notation, you'd probably write it as like minus infinity to infinity. Okay. Let's see what that was. Okay. That's a good question. I didn't quite write it down as a question, but in finding the domain of the tangent function, you probably want to find where the vertical asymptotes are. And then the domain is going to be like wherever it doesn't have a vertical asymptote. So let's maybe talk about that part right now, since we're trying to find some equations of some of the vertical asymptotes, okay? Okay. So let's first think about like the ordinary tangent function. Okay. So for like the ordinary tangent function, its vertical asymptotes are going to be at all of the odd multiples of pi over 2. So if you were to kind of write it out as like a list, it would have vertical asymptotes that say like negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, etc. Okay. So those are where all the vertical asymptotes of like the ordinary tangent function would be. Okay. And you can write it as kind of like a general formula, as like a, let's see here, something like 2n plus 1, and then times pi over 2, where n represents like any integer. Okay. All right. So that's kind of like the general formula for the vertical asymptotes of tangent. Okay. Now here for this problem though, we have a kind of a more complicated tangent function here. So if you want to find where the vertical asymptotes are for something more general like this, the idea is if you take what's on the inside of the tangent function, so in that case, we have a 4x plus pi over 4. So whatever is inside of your tangent function, if you set that equal to here, this kind of general formula that we had for the vertical asymptotes, for the ordinary tangent function. Okay. And then if you rearrange this equation and kind of solve for x, that's going to give you where all the vertical asymptotes are for your function, okay? So in this case, what I want to do is I want to maybe solve for x right now, so I would maybe subtract pi over 4 over first. Okay. And I'm going to go ahead and get a common denominator, I think. So I'll multiply this fraction on the top and bottom by 2. Just to get that common denominator. And then we're also subtracting pi over 4. I'm going to go ahead and combine these two fractions. And I think what I'll also do over here is I'm going to go ahead and distribute this into the parentheses. So I'm going to get 4n pi when I do that, plus 2 pi. And then we're also going to subtract a pi as well. That's all over 4. So that leaves me with 4n pi. And then 2 pi minus pi leaves me with 1 pi over 4. Okay. And so if I want to solve for x, I would then divide both sides by 4. Or if you will, I could multiply both sides by 1 over 4. That cancels these 4's out and leaves you with x equals, and then I think on this side, I'm just going to multiply this 4 into the denominator to get 16. And it's not a big deal, but maybe I'll do one more thing, which I'll maybe factor a pi out from both terms in the numerator. So maybe I'll write it as 4n plus 1 pi over 16. So these would be where all of the vertical asymptotes are for our tangent function here. Okay. So to kind of summarize how we got this, we took what was inside of our tangent function, and we set it equal to this expression here. So basically, this is representing the odd multiples of pi over 2. Once we set those equal to each other over here, then I just solved for x like that, okay? Now, I guess here we want to kind of follow the instructions specifically. It said to write down the equations for 3 consecutive vertical asymptotes. So we have this kind of general formula here. So if we just want to get 3 consecutive vertical asymptotes now, we could get 3 consecutive vertical asymptotes just by plugging in 3 consecutive integers for n into this formula. So just kind of an example, I'll plug in the numbers 0, 1, and 2. But you can choose any 3 consecutive whole numbers to plug into this formula to get 3 consecutive vertical asymptotes, okay? Now, when n is 0, if you plug in 0 for n, you'll be left with pi over 16. So that's going to be one of the vertical asymptotes. Next, I'll plug in n equals 1. That will go as 5 pi over 16. So that would be like the next vertical asymptote after pi over 6. Well, that should be pi over 16, right? Yeah, that's my bad, pi over 16. And then if I plug in n equals 2 into here, you'll get 9 pi over 16. and that would be the next vertical asymptote. Okay. So then here, this will give us like 3 consecutive vertical asymptotes. Okay. And as kind of like a side note then, to answer the question about what was the domain of our function. So the idea is the domain should be all real numbers except where we have a vertical asymptote. So you can maybe write it like this, like domain would be all real numbers except those numbers which are of this form, because these would be where you have the vertical asymptotes. Okay, so I guess I'll pause for a moment and open it up just to see if anyone has any questions.
How would you write the domain in like a range form?
Sure. So if you're thinking about writing it in integral notation, that'll be a little bit complicated. So if I were to write it, I'd have to use a union symbol. And let's see here. I think it would maybe look something like this, maybe. I mean, this is probably not, maybe your professor would write it differently, but I'm just thinking like, how would I try to write it using intervals? I think I'd have to do something like this. Oops, not plus, just times. Oh no, I see. Plus 1. Okay, let me rewrite that then. So what I'm doing is I'm taking this formula that we found for where the vertical asymptotes are. So I want to say that the domain is all real numbers in between all of these vertical asymptotes. So the way that I'm doing that over here is, what I've done is I took this formula and I replaced n with n minus 1 to get this expression over here. So like instead of 4n plus 1, I just replaced n with n minus 1. That was just to like represent like the vertical asymptote right before this one. So then this is like everything in between those two vertical asymptotes. But then I had like an infinite union because there will be infinitely many intervals because you have infinitely many vertical asymptotes. So I think that's maybe a bit much, but I think that's maybe how I would write it myself. But I don't think you guys would have to do that because I don't think you guys have really done much with like an infinite union or anything like that, okay? But yeah, since someone asked, I think it would maybe look something like that. So probably if you did have a question like asking about the domain, I think an answer like this would probably be more natural and probably just easier overall as well, okay? At least for a tangent, yeah. Any other questions?
Are we going to graph it now?
Yeah, as well, that's right. I just wanted to see if everyone was, kind of following along. But yeah, so the last part was to graph at least 2 periods of this function. So let's talk about how we would do that. Let me maybe recopy this. So then to graph this function, so I know that you guys usually construct like a table to like get some points that you can plot. And I think that's a good way to get a relatively precise graph. So I'm gonna kind of do what you guys do as well. Oops. So the way that you guys tend to graph your trig functions is you take whatever is inside your trig function. In this case, we have 4x plus pi over 4. And then I want to apply the tangent function to that. Okay. And what we do is in these two columns, we start by plugging in some, or we rather, I guess, we start by choosing some like of the nice angles for our trig function that are like useful to plot. And I know for tangent, let's see here. So I know for tangent between negative pi over 2, whoops. And pi over 2, whoops. I know that that creates one period. Okay. And I know that tangent, like the ordinary tangent function, it has a vertical asymptote at negative pi over 2 and also at pi over 2. And I know that tangent of negative pi over 4 is negative 1. Tangent of 0 is 0. And whoops, I thought it was supposed to be a 4. And tangent of pi over 4 is positive 1. So for like tangent function, these are kind of like some of the nice points on its graph. All right. And so this is going to kind of plot out one period right now. But what we need to do, yeah, so for tangent functions, I would recommend choosing those numbers, or those angles rather. And then what you guys have to do is you have to kind of work backwards from here to solve for x. So let's say if we wanted to solve for x, we'd have to subtract pi over 4 from everything first, okay, to get 4x. So let me go ahead and subtract the pi over 4 from everything here. I think that will give us minus 3 pi over 4 for that one. I'm going to subtract pi over 4 from everything, and that should become minus pi over 2. Subtracting pi over 4. And then here, subtract pi over 4 gives us 0. And pi over 2 minus pi over 4 gives us pi over 4, okay? And I'm working backwards to solve for x. So right now, this is 4x. So to get to x, we'd have to divide by 4 after that. Or if you will, dividing by 4 is the same as multiplying by 1 over 4. So then if we multiply all of these angles by 1 over 4, that will give us minus 3 pi over 16 minus pi over 8 minus pi over 16, 0, and pi over 16, okay? Okay. And then, so we solved for x by working backwards, and then over here we need to transform this into our function now. Okay. So from this tangent, we'd have to multiply it by 2. Okay. So here we're going to multiply everything by 2. Now, for the vertical asymptotes, you don't really get anything by multiplying by 2. So just remain vertical asymptotes. Here, multiplying by 2 gives you negative 2, 0, and 2. Okay. Then we're just going to do one more thing, which is to transform it to our function. We just need to add 1 to everything now. Yeah, so we started with the 4x plus pi over 4 because that's what we had inside the tangent function. And whatever you have inside the tangent function, I think these are like a good set of angles to work with to plot out like one full period. Reason why is because tangent had nice values each of these angles. So I'm not too sure if that answered your question, but generally whatever you have inside your tangent function, you'll make that a column, and then I would recommend using these angles myself in that column. Yeah, and then if it's undefined, if you have a vertical asymptote, then like multiplying by 2 or adding 1, things like that aren't going to change that. So these will remain vertical asymptotes. And then let me see here. We added 1 to everything, so we get -1, 1, and 3 after adding everything, okay? Now to create your graph, you want to focus on the x column and then the final column for your function, okay? So the x column gives us like all the x coordinates, and then this gives us the y coordinates of some of the points on the graph. Yeah. Okay. So let me go ahead and kind of set up a picture for this now. Okay. So let's see here, at -3 pi over 16, which I'll just kind of mark out here maybe. We're going to have a vertical asymptote. And then let's see, we've got a minus pi over 8. Let's say this is minus pi over 16. Let's say that's a 0. And then let's say this is pi over 16. And here's another vertical asymptote. Let me add in my vertical axis here. Okay. And let's see here, at negative pi over 8, the function should be equal to -1. Let's maybe mark -1 around, I think it'll be somewhere down here-ish or so. So let's mark that as -1. So we'd have +1 about out here or so, 2, 3. Okay. And then let me see. So when x is negative pi over 8, the function should be passing through this point here, where phi being -1. When x is negative pi over 6, it's going to be equal to 1. So it'll be up here. And then when x is 0, the function is going to be up here at 3. Okay. And then I'm going to try to draw a picture of this now. So then tangent, if you guys remember, this graph looks something like this. Let's pretend that passed through that point. It's going to go through here. It's going to become kind of flat, and then it's going to shoot up again, passing through that point, and then it's going to go up after that. Okay. So right now, that's going to be one period of the tangent function. Try to shrink that a little bit. Okay. And then if you want to graph another period, you can just kind of imitate what we just did. Oops. Okay. So then next we have a point at -1, +1, and 3 here or so. And then we should have a vertical asymptote here again. Okay. And that's kind of just a rough sketch of two periods for this tangent function. All right. So do you guys have any questions about how I made that graph, or just anything else about this problem? Okay. For this tangent function, yes, there would be a phase shift. Okay. Oh, right, I see. Okay. Okay, so for the phase shift, so I guess the phase shift would be the same for all the trig functions. So it doesn't matter which kind of trig function it is. Who remembers the formula for the phase shift? Yeah, good. So yeah, the formula for the phase shift, whether it's tangent or any other trig function, if you have like a bx plus c on the inside, the formula for the phase shift is going to be c over b. Okay. And then you can determine if it's like shifting left or right, depending on whether it was a plus or minus. So it shifts to the right if it was a minus, and it shifts to the left if you had like a plus, right? Okay. Okay. All right, so let's go ahead and move on to the next problem then. So we want to, everyone voted for looking at the graphing a tangent and then graphing a secant. So let's take a look at this one next. Oh, what was that? Yeah, so I think it looks like you guys use the rotation bx minus c. That doesn't make a big difference in the end though, whether it's plus or minus. Okay. The phase shift will still be like c over b. And you'll still know whether it shifts, like which direction it shifts in based off the sign is the idea, okay? But yeah, so it looks to be bx minus c though, so I'll go ahead and use that notation as well. Okay. Let's take a look at graphing this secant function next. Okay. Let's see here. So let's maybe talk about the ordinary secant function real quick then. So we just like a secant of x. Okay. Right, so for the ordinary secant function, it has a period of 2 pi. Who remembers what the range of like the ordinary secant function was? Okay. So the secant function, all right, so it had a range from -infinity to -1, and then also from 1 to infinity. Okay. Yeah, very good. Its graph looks something like this. I'll just draw like one period of it. So it's 1 over cosine. So secant has some vertical asymptotes. It has vertical asymptotes at the same location as tangent. Okay. So all the vertical asymptotes of secant are at all the odd multiples of pi over 2. Okay. So at negative pi over 2, pi over 2, and 3 pi over 2, that would be like 3 consecutive vertical asymptotes for the ordinary secant function. And then the graph looks something like this, where it opens up and then it opens down in between like 2 consecutive vertical asymptotes, and then it's going to repeat this after that. Okay, so this would be one period of the ordinary secant function. Okay. Now here, more generally, for something like this, the period, instead of being 2 pi, is going to be 2 pi over b. Okay. Which in this particular problem would be 2 pi over 3. Okay. Okay. Now, for the range of this function, let me go ahead and come back to that part. Maybe it'll be nice to actually graph it first. And then once we graph it, we can maybe talk about what the range was based off the graph, okay? So I'm going to come back to this one. You guys might know the answer just by looking at it, but I think some people may be more visual and might prefer to see the graph first. So I'm going to graph it first, okay? And now I'll come back to answer what the range was. Okay. I guess let's talk about the vertical asymptotes first, and then we'll talk, try to graph it, okay? So for the vertical asymptotes, I'll do kind of similar to what I did with the tangent function earlier. So to get the vertical asymptotes, you take whatever is inside your function. So in this case, inside of our secant, we have 3x plus pi over 2. And I'm going to set that equal to where the ordinary secant function has vertical asymptotes. So you can set it to this general formula. Okay. And then from here, to get the equations, you want to actually solve for x now. So the first thing I would do is maybe subtract pi over 2 to the other side. Okay. Here, let me go ahead and distribute the pi over 2 into the parentheses. So when I distribute to the 2n, the 2's are going to cancel. When I distribute to the 1, I'm going to get plus pi over 2, which will cancel with this minus pi over 2. So that's kind of nice. Okay. Oh, well, okay. So that leaves us with that 3x equals n pi. So solving for x, you get x equals n pi over 3. So this would be kind of the general formula for where all the vertical asymptotes of our function will be. And then to get 3 consecutive vertical asymptotes, again, just plug in 3 consecutive numbers for n. So I'll do 0, 1, and 2. But you could do like 1, 2, 3, or any other 3 consecutive numbers. All right, so when n is 0, you get x equals 0 as one of the vertical asymptotes. When n is 1, you get x equals pi over 3. And then when n is 2, you'll get x is 2 pi over 3. So that would be 3 consecutive vertical asymptotes in particular, okay? All right. Now let's talk about actually graphing this function now. So I'll do something similar to what we had before, where we'll create a little table. Okay. And to start with, I'm going to create a column for whatever is inside of our function. So 3x plus pi over 2. Okay. Let me see what that was. What happened to the 2n plus 1? Okay, so over here. So what I did was I distributed the pi over 2 into the parentheses. So when you distribute pi over 2 to the 2n, the 2's canceled. So that left us with n pi. And then when you distribute pi over 2 to the 1, it gives you the plus pi over 2 that I had here, okay? All right, does that answer the question? Okay, cool. Let's see here, okay. And then let me see here, so I'm graphing this function. Okay, so here I started with what was inside of the secant function. Now for me, I'm more familiar with sine and cosine than the other trig functions, so I like to do sort of an intermediate step before I go to secant, which is I like to look at cosine first. Because I know that secant is 1 over cosine. Okay. So you don't necessarily have to do that, but it's just kind of my personal preference because it's easier for me to dig up cosine and to get secant by doing the reciprocal, okay? Now for a cosine function, I think it's a good choice of angles to work with. Maybe just the usual 0 to 2 pi, and I'll go up in increments of pi over 2. So we know that cosine makes one full period from 0 to 2 pi. So I'm just going to use that as my starting point. And then I know cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine 3 pi over 2 is 0. And then cosine 2 pi is 1, okay? Okay, now secant, we know is the reciprocal of cosine. So I'm just going to do the reciprocal of all of these values to get secant. Okay. So here we're going to get 1 over 1, which is 1. Now here, if I do the reciprocal, we'll get 1 over 0, which is undefined. So what's happening is whenever cosine is equal to 0, secant has a vertical asymptote instead, okay? So then likewise down here, that 0 for cosine means that you have a vertical asymptote for secant. And then here, if I just continue doing the reciprocal, 1 over -1 is still -1, and 1 over 1 is still 1. Okay. Okay. All right. So then from here, I need to subtract 2 from this to get to our function. So I'm going to minus 2 from all of these values. So 1 minus 2 is -1. -1 minus 2 is -3. 1 minus 2 is -1. And then you still have vertical asymptotes at these locations. Okay. Okay, and then likewise over here, I want to work backwards to solve for x. So the first thing I would need to do is subtract pi over 2 from everything to get to 3x. So subtracting pi over 2 from everything will give me minus pi over 2. And then pi over 2 minus pi over 2 is 0. Pi minus pi over 2 is pi over 2. 3 pi over 2 minus pi over 2 is pi. And then minus pi over 2 gives me 3 pi over 2 down there. Okay. Okay. And then I want to solve for x, so I still want to divide everything by 3 or multiply everything by 1/3. Okay. So I'm going to multiply everything by 1/3, and that's going to leave us with minus pi over 6, 0, pi over 6, pi over 3, and 3 pi over 6. So I guess we could simplify as pi over 2. Okay.
Can you explain why we used cosine?
Sure. So that's just because it's easier for me personally to think of cosine. And then once I figure out what cosine is, I know that secant is 1 over cosine. But you don't have to do it that way, though. You can jump straight to secant as well if you're comfortable doing that. It's just for me personally, I like to insert that little step in between because I can think of cosine much more easily than secant. Okay.
Got it.
Okay. All right. And let's see here. Okay, so then we completed the 2 columns that we really needed. So the columns we needed were the x column here, and then the final column for our function. So with this information, we should be able to sketch one full period. So I'll try to do that down here. So let's start with minus pi over 6, 0, pi over 6, pi over 3, and then we had pi over 2. Let me draw my y-axis here. Okay. And I guess I'll go down a little bit more. Okay. Let's see here. We had vertical asymptotes at 0, and then also at pi over 3. Okay. So I'm drawing my vertical asymptotes here first. Okay. And then I have some points at -1, -3, -1. Okay. So let's maybe mark this as -1. Oops. Let's say that's maybe -3 down there. Okay. And then at minus pi over 6, the function was at -1. So I'll draw that here. See here at pi over 6, it's at -3, so that's going to be down here. And then at pi over 2, it was at -1 again. Okay. And then let me go ahead and add a couple more vertical asymptotes in this picture. Okay. And then knowing what the ordinary secant function looks like. So if you'll remember, I'll come back to here real quick. So secant opens up and then it opens down like that. So kind of with that in mind, I'm going to similarly over here at the -1, it should be opening up. Okay. So I'm just going to kind of draw something like that in this picture. And then here it'll be opening down. Okay. And up here it should be opening up again. So it should be something like that. Okay. And let's see here. I guess this would have given us kind of one period. So if we want a second period, I should maybe imitate the bottom one more time. So let's maybe go like that. If we needed to, and then that would kind of be like a second period in the picture. Okay. And then let's see here. Okay. All right, there you go. Okay. So then let's go ahead and pause for a moment. So, oh, okay. So maybe first, any questions? Okay. So then let's just go back to answer real quickly what the range of this function was. Because I actually skipped that part of the problem. All right. But here, I guess once we kind of finish the graph of it, so you see that the range up here, it starts at -1 and goes out to infinity. And we also have this portion down here where it starts at -3 and goes down to -infinity. So we have one interval from like -infinity up to -3. But then we have another interval starting at -1 and then going up to infinity. Okay. So that would have been the range of this secant function here. Now, I thought it would be nice to actually have the graph first so that you can then kind of see what the range was based off the graph. But I'll go ahead and make a quick comment as well for how you could have gotten that, without actually graphing it. So if you know that the range of the ordinary secant function is -infinity to -1, and then 1 to infinity, as we kind of talked about earlier. What happened is we had a vertical shift where we shifted down by 2 units. And it's because we had that vertical shift down by 2 units, we had to shift these intervals down by 2 units as well. So like -1 and then -2 gives you that -3 down here. And likewise, the +1 here, if you subtract 2 from that, it gets you that -1 that we have here, okay? So kind of more generally, if you have a vertical shift, if you just sort of apply that to the original range, that will give you like the new range for your new function, okay? Okay. All right, so we spent quite a bit of time actually talking about graphing some trig functions. I kind of felt that would take a long time, so that's why I only wanted to do 2 examples. And look at just some of the other things that I have prepared for this review. And then I can always go back at the end and talk a little bit more about graphing if you guys have more questions about it, okay? All right, well, let's go ahead and move on for now. Okay, so I have a couple parts which involve evaluating some trig expressions. So here I've got just some expressions involving the usual trig functions. So we want to evaluate some of them. So I'll do a few of these problems here. And then I also have something similar, but involving the inverse trig functions as well, okay? Okay. So let's look at this second part here, and let's maybe do 1 or 2 of these questions, okay? All right, so to answer these questions here, these are all like really based off your knowledge of the unit circle. So you'll just need to kind of know, where are these angles in the unit circle? What are the values of like sine, cosine, tangent, etc. At those angles? Those are things that you'll kind of need to know. So my recommendation is if you haven't really familiarized yourself yet with the unit circle, like how to like memorizing at least part of it, and then like how to use your knowledge to figure out the rest of it. That's definitely something that I would recommend that you do, because that just makes all of your problems much easier to solve if you know the unit circle pretty well, okay? Let's do maybe, let's just look at maybe C and D for this review right now, okay? So let's take a look at C first, okay? So we're trying to evaluate secant of 3 pi, and then plus 3 root 3, and then we have cosecant of 4 pi over 3, okay? Okay. Okay, so let's look at the secant of 3 pi first. Okay. And so first, I know that 3 pi, so thinking about where would the angle 3 pi be located. So remember, if we start at 0, pi would be here along the negative x-axis. And then if you go around again, you would reach 1 full revolution with an angle of 2 pi. And then if you go around another 180 degrees or pi radians, you see that 3 pi corresponds to the same direction as pi, okay? So then thinking about, say, the unit circle, this point here at that angle of 3 pi would have the x component -1, y component 0. And I know that secant is 1 over cosine, right? And I know that cosine is the x coordinate. Whoops. Okay. So cosine of 3 pi should be -1. So therefore, secant of 3 pi should be 1 over -1, which of course is just a -1. Now then, this one's maybe a little bit harder to think about, but let's see. So I know that 4 pi over 3, so thinking about that, it's a little bit more than pi, so it puts me in the third quadrant. And let's see here, at the pi over 3 angle, let's see here, I know the x is 1/2, the y is negative root 3 over 2. Okay. And then I know cosecant is 1 over sine, so sine corresponds to the y coordinate. So sine of 4 pi over 3 should be negative 2 over root 3. So cosecant, though, is the reciprocal. So cosecant should instead be negative root 3 over 2, okay? Oh, whoops, I did that backwards. I was thinking ahead, I suppose. Sine is minus root 3 over 2, and then cosecant is the reciprocal of that, so 2 over root 3. So that's my bad, I was thinking ahead. Okay. So then if we just want to simplify that a little bit, so over here, the square root of 3's will cancel out. So you'll really just be left with 3 times negative 2, which is negative 6. So it looks like this expression will evaluate to be negative 7. Okay? All right, so then do you guys have a question about that? Okay, all right. Do you guys want me to do part D as well? Or do you guys want to spend more time, say, looking at some of the inverse trig functions instead? So maybe I'll leave that as an option to you guys. You want to see one more of these problems? Or do you maybe feel more like, do you maybe want to spend more time with inverse trig? Okay, cool. So let's do one more of those. So I think maybe the hardest one was maybe D, I suppose, or at least that was the longest one. So we'll look at D next. Let me try to back down. Oh, damn. There you go. Oh, wait a second. Why did I copy that one? I must not have copied it then. So Control C. And then Control V. Okay, finally. Then yeah, let's look at this last one here. So you've got 5 cotangent of 5 pi over 4. And then we have minus 4 cosine 2 pi over 3. And we have plus 3 cosecant 7 pi over 6, okay? Yeah. All right. Now let's see, I know that, let's start with the angle here first. So I'm going to start with this first expression, 5 pi over 4. So which quadrant would 5 pi over 4 be in? First, second, third, or fourth?
Third.
Yeah, that's right. And pi over 4 is kind of like your 45-degree angle. So that means it's kind of like right in the middle. Okay, good. So since it's like right along the middle, I know the x and the y are the same. And I know that for the pi over 4 angle, they're both like √2 over 2. Okay. And then, of course, in the third quadrant, they would both be negative as well. Now, remember that here we have cotangent. So I remember that tangent is like y over x, meaning that cotangent would be x over y. So here, if we do the x-coordinate over the y-coordinate, since they're both the same, they would just cancel out. So cotangent 5 pi over 4 should just be equal to 1 altogether then, okay? So maybe I'll kind of write that out just to be sure we can see that. So it's the x-coordinate, which is minus √2 over 2, but then over the y-coordinate, which is the same. So they'll completely cancel out, leave you with a 1 over 1, which is just 1, okay? All right. So let's look at this next one over here then, where we have cosine of 2 pi over 3. So 2 pi over 3, let's see here, that would be in the second quadrant. It's a pi over 3 above pi. So that pi is here, 2 pi over 3 would be 60 degrees, or pi over 3 before that. And so I know here the reference angle is pi over 3. So I know that at the pi over 3 angle, it was 1/2 for the x, and it was √3 over 2 for the y. But in the second quadrant, x is negative, okay? And then cosine of 2 pi over 3, cosine is the x-coordinate. So that means it would be equal to negative 1/2. Okay? And then lastly, if I want to think about cosecant 7 pi over 6. Yeah, so 7 pi over 6 is going to be in the third quadrant. So it's pi plus pi over 6. So it's kind of like 30 degrees more than 180. It's just a little bit past pi. And so I know this will be similar to the pi over 6 angle. And for the pi over 6 angle, the x is √3 over 2. The y was 1/2. And then in the third quadrant, they'd both be negative. Now I know that sine is the y-coordinate. So sine of 7 pi over 6 would be negative 1/2. But cosecant is the reciprocal of sine. So it would be negative 2 over 1, or just negative 2, okay? From there, we'll get 5. This would be plus 2. This would be minus 6. That would be 7 minus 6. So the answer is going to be positive 1, okay? Okay. So really, to work these out, you have to have a pretty good knowledge of the unit circle in order to work it out, okay? Okay, let's take a look at some of the inverse trig functions next, or inverse trig expressions. Okay. So I'll do a couple of these problems. I'll just pick and choose a little bit.
Can you do the composite functions?
As in kind of the latter half, you mean, right? I guess.
Yeah.
Okay. Yeah, we'll do a couple of those then. Let's see here. Let's do, just kind of pick at random. Let's do this one. Maybe this one. Oh, what the heck? Let's try to do, well, I don't know if I'll do all three of them, but I think those are all maybe good. Maybe we can do maybe one or two of these as well. Let's do maybe this one and maybe whatever, this one. Okay. I'm just kind of picking and choosing a few. Okay. All right. So let's look at, I'll do maybe D first. Okay. So this is the inverse cosine of minus root 2 over 2. And just kind of a quick note, this cosine to the -1 notation, that's often written as arc cosine as well. So you might see this notation like cosine to the -1 for the inverse cosine, but you might see arc cosine instead. Those are the same things, okay? And worth noting, because I see this a lot, when you have cosine to the -1 or something like that, that's actually not the same as 1 over cosine. So when you ever have a trig function to the -1 like that, you should never interpret it as like the reciprocal, okay? All right. Okay, so let's talk about how the inverse trig functions work. So we'll start with inverse cosine because that's what we have in this problem. So all of the inverse trig functions output an angle. So let's see here. So when you have the inverse cosine of something, that gives you an angle, and you need to think about which angle that would be. So the cosine inverse of x equals theta. That's equivalent to saying cosine of theta is equal to x. Okay. Here, the way I think about it is I kind of think about like moving the cosine inverse to the other side. But when you move it to the other side, it becomes an ordinary cosine. So it's like cosine of theta equals x. Okay. Now, on the other hand, with all the inverse trig functions, so they give you an angle, and they always give you an angle in a certain range. So I know for inverse cosine, the angle has to be in the range from 0 to pi. Okay. And I'll talk about the range of the other inverse trig functions as I encountered them in the other problems. Okay. All right. So here, what I want to think about to answer this question is, what angle theta will cosine of theta be equal to negative root 2 over 2? And specifically, what an angle that satisfies this and is between 0 and pi.
Pi over 4.
Close, but I think
Oh,
pi
no.
over 4 cosine would be positive,
Negative.
right? So
3 pi over 4, actually. 3 pi over 4.
yeah, that's right, yeah. So you have to move to the second quadrant, and 3 pi over 4 would give you this value. So the inverse cosine of minus root 2 over 2 is going to be 3 pi over 4, okay? All right, good. So let's look at, let's look at E next real quick. And then I'll start doing some of the more composite ones after that. Yeah, so E, we have the arctangent, or the inverse tangent of root 3. Okay. So we'll talk about inverse tangent now. So inverse tangent, again, it gives you some angle data. Now the angle has to be in the range from minus pi over 2 to pi over 2 for the inverse tangent. And then likewise, when you say tan inverse of x equals theta, that's kind of the same as saying that tangent of theta is equal to x, okay? So again, it's kind of like moving the tangent to the other side of the tangent inverse, but it becomes ordinary tangent when you move it over. Okay. So for this problem then, to answer the question, we need to think about what angle theta will tangent of theta be equal to square root of 3, where that angle theta is also between minus pi over 2 and pi over 2. All right. So then I know that tangent will be equal to square root of 3 at an angle of pi over 3 in the first quadrant. Okay. And pi over 3 does fall in this range, okay? So then the answer to inverse tangent of root 3 would be pi over 3. Okay. Let's see here. Let's look at maybe H next, okay? Where we have a sine inverse of sine of 5 pi over 3. Okay. Now, I guess there's a couple of ways you can think about this problem here. You don't necessarily have to do this, but it might seem easier to do it first. So, you know, we have sine of 5 pi over 3 on the inside. So maybe you can tell me what sine of 5 pi over 3 is equal to.
Negative root 3 over 2.
Yeah, to pi over 3 angle, fourth quadrant, so negative. Yeah, I agree with that. So first, all we did was evaluate the inside. So we just said sine of 5 pi over 3 is negative root 3 over 2. Okay. Okay, so now to evaluate this expression here. So inverse sine, just like all the other inverse trig functions, it outputs an angle. Now for the inverse sine, that angle has to be between minus pi over 2 and pi over 2. And then this equation, you can kind of rearrange it if you kind of, again, move the sine inverse to the other side. When you move it over, it becomes an ordinary sine. So we have that sine of theta should be equal to x. Okay. So here I want to think about for what angle theta is the sine of theta going to be minus root 3 over 2. And it can't just be any angle. It has to be an angle in this range from minus pi over 2 to pi over 2. Okay. Okay. Okay, now I know that sine is going to be equal to root 3 over 2 at the pi over 3 angle. But if I want sine to be negative root 3 over 2, I would need to go down into the fourth quadrant for that. So if I kind of go clockwise at an angle of pi over 3 as well. Remember that going clockwise makes the angle negative. So if we go clockwise pi over 3, that gets us to the angle minus pi over 3. So then sine of minus pi over 3, now that we're in the fourth quadrant, sine becomes negative. Okay. So the angle in this range that satisfies this equation is the angle minus pi over 3. Okay. So therefore, the inverse sine of minus root 3 over 2 is the angle minus pi over 3. Okay.
I don't
Yes.
understand. Why is it shouldn't it be 5 pi over 3?
Yeah, so that's a good question. So you were maybe thinking the answer was 5 pi over 3 because that angle, sine of 5 pi over 3 is already equal to minus root 3 over 2. Okay. The reason why the answer is not 5 pi over 3 though is because of this kind of range restriction on the angle for the inverse sine. So inverse sine has to give an angle in this range. So the problem with the 5 pi over 3 is that it is actually not in this range. And that's why that would not have been the correct answer because of that, okay? So you want to be a little...
But if there was no range, then 5 pi over 3 would be the answer?
Well, okay, so if there was no range, so as kind of a brief aside, so if you were just looking at this equation, like sine of theta equals minus root 3 over 2, and there's no restriction on the angle theta, then I guess, 5 pi over 3 would be one solution. As well as like negative pi over 3. There would be a lot more solutions to that as well. So there's like more than one angle which will satisfy an equation like this. So the issue is when you're dealing with the inverse trig functions, they always have a range restriction. So it kind of forces you to look for one particular angle that satisfies that equation and then in that range restriction, okay?
Yeah, got it.
Okay, all right. So then, yeah, let me kind of highlight these. So we talked about kind of the range restriction for inverse cosine and inverse tangent and inverse sine. So we can note of all of those right now. Let's continue looking at a couple more of the problems. Okay, so these last couple problems are maybe a little bit different from the ones that we've seen previously. Let's look at J first. So it's cosine arctangent of 4. Okay. So here what I'm going to do is, so maybe it's kind of similar to the last one. I'm going to just focus on what's on the inside first. So on the inside, we have this inverse tangent of 4. Now, inverse tangent of 4 returns an angle theta. And this angle theta satisfies tangent of theta equals 4. So I kind of get that by maybe thinking about moving the tangent inverse over. But when you move it over, it becomes the ordinary tangent. And then I know the inverse tangent also has a restriction that the angle is between minus pi over 2 and pi over 2. Now here, 4 is not like one of the like nice values of tangent. So we don't actually know the exact angle that satisfies this equation. So what I'm going to do instead to kind of help me out with this problem is I'm going to draw a little bit of a picture. So here I'm going to kind of think of it as tangent. Let me write it down here real quick. So if I think of tangent as being y over x, okay. And then we also have tangent and data, in this case being 4, which I can think of as being 4 over 1. Okay. So what I'm going to do is I'm going to draw a picture with the angle data where it'll pass through this point where the x is equal to 1, the y is equal to 4. So let's try to plot this point where x is 1, y is 4. Okay. So this angle data should be an angle that looks kind of like this. Okay. Now with this angle data, we're trying to figure out what the cosine of this angle is. Okay. So tangent inverse of 4 gives us some angle data. We have a picture of what data looks like. And so from this picture here, we want to try to figure out what cosine of data is going to be. So to figure that out, I want to make use of this like right triangle that we have. Okay. So here, I know that cosine is like adjacent over hypotenuse, right, for a right triangle. And in this right triangle for data, we know the adjacent side is going to have a length of 1. We don't know the hypotenuse just yet, but we can figure it out using the Pythagorean Theorem. So we know that 1 squared plus 4 squared should give us the hypotenuse, which I'll call c squared. So that gives us 17 equals c squared. So c, the hypotenuse, will be square root of 17, okay? So then knowing the hypotenuse is square root of 17, that leaves us with the final answer of 1 over root 17 then, okay? Okay. So for this problem, slightly different from the other questions because we had, well, so I would say there's maybe 2 things I would say that are kind of different about this problem from the others. So the previous 3 questions were just evaluating an inverse trig function like that. Here it's a little bit different because if you compare with maybe H, you had the inverse trig function of a trig function. Here it's kind of flipped where you have a trig function evaluated at an inverse trig function. That's kind of one difference is where the inverse function was is kind of swapped. And then also the number that we had was like not as nice of a number. So we had to kind of resort to drawing a picture of a triangle since we couldn't figure out the angle exactly, okay? So the last 2 problems are kind of similar to J as well. So let's take a look at how the last 2 problems will work as well. So they'll be kind of similar. We have cosecant and then cosine inverse. So cosecant, and then the cosine inverse or the arccosine, and it was 7/9, okay? All right, so yeah, for this one, we'll have to kind of draw a similar picture. That's a good question, actually. Let me address that question. I can address it right now. It's a pretty quick one, okay? Yeah, so someone asked if you had arccosine. Oh, actually, well, that's not quite what I was thinking, but I guess you can still address it real quick. So arccosine of cosine, and it was 17 pi over 5. Okay. Yeah, so the issue with this right now is that 17 pi over 5, that is not one of your usual angles that you kind of have like maybe memorized on the unit circle. Okay. Okay, so let me think about this. First, 17 pi over 5, let me think about maybe which quadrant that would be in. So 17 pi over 5, that's a little bit more than 15 pi over 5. And I know 15 pi over 5, that's just going to be 3 pi. So I'm just kind of thinking to myself, where is this angle first in the picture? So I know that 3 pi is going to put me all the way out here. So we're adding 2 pi over 5 to that, so it's out a little bit more. So it'll kind of be maybe around here or so. Okay. Okay, so next, let me think. So I know that arccosine in general, like all the other inverse trig functions, it's going to be an angle. Okay. Now that angle theta has to satisfy two things. So first is cosine of this angle should be equal to this value here. So again, I get this equation just by kind of thinking about moving the inverse cosine to the other side. But again, whenever you move it over to the other side, it becomes an ordinary cosine. Okay. And then, let's see here. But we also know that the angle that inverse cosine outputs has to be in a certain range. And for inverse cosine, the range was 0 to pi, okay? Okay, so I know that cosine corresponds to the x-coordinate of a point on the unit circle. So I want to find an angle where the x-coordinate is the same as this point here at 17 pi over 5. So there's another angle in the second quadrant up here that would have the same x-coordinate. So I want to think about maybe what angle in the second quadrant will share the same x-coordinate as 17 pi over 5 as that point down there, okay? And to figure out what that angle is, well, I know that this angle here was 2 pi over 5, because remember we figured this out by doing 3 pi plus 2 pi over 5 to get to 17 pi over 5. So kind of by symmetry, I would want to go backwards 2 pi over 5 as well to figure out what this angle is going to be. So theta, I can say I want it to be in this range, so I'm going to take pi, so this angle of pi here. I'm going to subtract that 2 pi over 5 to figure out what the angle theta would be. So in this case, it seems to give me an answer of 3 pi over 5. Okay. So then that would be the inverse cosine of cosine 17 pi over 5, okay? So that one's maybe a little bit tricky then, actually, because it's not an angle on the unit circle. But I got a sense for where that point is located in the picture. I figured out it was kind of in the third quadrant. It was 2 pi over 5 more than 3 pi. Okay. So then I'm thinking I want an angle theta where cosine of that angle is the same as cosine of 17 pi over 5. So I was thinking in terms of the x-coordinates, because I know cosine corresponds to the x-coordinate. So then to figure out this angle, I used the idea that this angle was 2 pi over 5. So this angle here was also 2 pi over 5 by symmetry. And then I had to subtract that from pi to figure out the angle theta, okay? All right, so I hope that was clear enough. Is that good? All right, cool, all right. All right, we'll do a couple more inverse of these problems. Maybe I'll do K at least, and then maybe look at L, or I might jump to something else instead, because there's a couple more things I wanted to cover as well. Okay, so let's look at this problem next. So we have cosecant of cosine inverse 7 over 9. Okay, so I want to start with the inside. So cosine inverse of 7 over 9. So I know this is going to be an angle theta. If you move the cosine inverse over to the other side, you'll get cosine of theta should be 7 over 9. And then cosine inverse gives an angle in this range from 0 to pi as well. Now, I guess since we have cosine of theta is 7 over 9, so for cosine to be positive, and between 0 and pi, this is going to be an angle in the first quadrant then, because cosine is positive there. So I'll just kind of draw a picture. We have some angle in the first quadrant, theta. And if I think of cosine as being the adjacent over the hypotenuse, then what I can do is I can label the adjacent side as 7 for this right triangle, and the hypotenuse I can label it as 9 right now. Okay. Okay, all right. So now that we know what this angle theta is, or at least we don't know the angle exactly, but we have a picture of it. Okay. And I want to know what is the cosecant of this angle. Okay. So then in terms of triangles, well, since sine is opposite over hypotenuse, cosecant would be hypotenuse over opposite then, okay? So yeah, so we need to use the Pythagorean theorem to figure out the opposite side now. So if we do 7 squared plus y squared is 9 squared. Yeah, okay. So y squared would be, oh, what is that? 81 minus 49. I think it's 32. And so yeah, so then when you square root that, square root of 32, which I think you guys simplified as well. Okay. So yeah, so that can be 4 times square root of 2. Very good. So then hypotenuse was 9, and opposite was 4 root 2. So then that will give us the final answer for that one, okay? All right. Let me just take a look at part L real quick. Yeah, I think part L is maybe worth looking at because it has a secant inverse in it, which I think we haven't done yet. Tangent, secant inverse, and 13/6. Okay. So let's see here, secant inverse. So I'm going to start with the inside again. So secant inverse, like all the other inverse trig functions, it gives you an angle theta. Okay. So whatever this angle theta is, we're looking for a tangent of theta right now. Okay. Now to get a better sense for this angle theta, I'm going to move the secant inverse to the other side. That'll give me secant of theta should be equal to 13/6. Okay. Now on the other hand, secant inverse has its own restriction on the angle theta. So secant inverse, secant is 1 over cosine, should be similar to cosine. So it should be restricted between 0 and pi, okay? So let's see here. I want to draw a picture of this. So between 0 and pi, so either in the first or the second quadrant. But since we have secant is positive, it has to be something in the first quadrant then, because that's where everything is positive. So let's kind of draw a picture of an angle theta in the first quadrant. Yeah, so for inverse secant, it should be strictly between 0 and pi. So similar to tangent earlier, if I scroll up real quick. So inverse tangent also had a strict inequality in it as well. So the reason why these other ones will have a strict inequality is because it's kind of related to the vertical asymptotes, if you will. So tangent had a vertical asymptote actually at minus pi over 2 and pi over 2. So that's why we have a strict inequality there. Theta could not actually equal one of those two angles. And it's kind of similar here. So the secant function has vertical asymptotes. Oh, wait a second. This is secant. I think I got that backwards. Oh, no, that's fine. Yeah. So secant actually does not have vertical asymptotes at 0 or pi, but okay, so then actually no, secant is actually good for those, but instead, the restriction on secant is that theta can't be equal to pi over 2 though. Okay. Yeah, thanks for that correction. So yeah, so secant was a little bit different, and I just wasn't thinking enough on that. So no, for secant, it is less than or equal to at the endpoints, but theta cannot equal pi over 2 because secant has a vertical asymptote at pi over 2 instead. Okay. Okay. All right, yeah, great. Okay. So then let me see here. Okay, so I was drawing a picture of the angle theta. So I figured it was in the first quadrant because we have secant is positive. So to be positive, that places it in the first quadrant. And then let me think, secant is the reciprocal of cosine. So I want to think of secant as being the hypotenuse over the adjacent then. So I'm going to kind of have a right triangle where I'll label the hypotenuse as having a length of 13, adjacent having a length of 6. From there, we need tangent of this angle, tangent being opposite over adjacent. Okay. So we'll need to figure out the opposite side real quick. So 6 squared plus y squared is 13 squared. That's 36. That's 169. So if I subtract 36 over, should be y squared is 133, I believe. So y will be the square root of 133. Okay. All right, thanks. So then now that we have that, to finish the problem, this will be equal to opposite is root 133 and adjacent is 6, okay? All right, cool. All right, so let's go ahead and move on to the next part. There's kind of 2 more parts that I wanted to cover. So one part just looking at proving some trig identities, and then the last one was solving some trig equations. So I am recording this review, so I will be uploading it to our YouTube channel later tonight. And I'll email everyone either later tonight or early tomorrow morning a link to the recording. And in the details of the video, I'll try to include like my work that I've done for this review, so you can kind of reference it as well, okay? Okay. So sure, since there was a request for it, maybe I'll skip the trig equations for now, but I'll go back to trig identities as well after that, okay? So I have a couple of equations here to try to solve. Maybe let's look at maybe 2 of these right now. Let me think here. Let's maybe do, let's at maybe B and maybe D first, okay? And we can maybe look at another one as well, but let's start with these 2. Okay. So in part B, we have a cotangent of 2x equal to 1 over root 3. Okay. So I guess the first thing you can maybe think about is for what angle theta, what cotangent of theta equal 1 over root 3. Okay. And this is not, you don't necessarily have to do this, but for me, I am a little bit more familiar with tangent rather than cotangent. So let me maybe like reciprocal both sides so that we can say tangent of theta should be equal to root 3 over 1 or just root 3, okay? So I just kind of did the reciprocal of both sides because I find it easier to think in terms of tangent personally. Now, tangent of theta, I know is going to be equal to root 3 at an angle of pi over 3. Okay. So this is an angle in the first quadrant. but I know the tangent is also positive in the third quadrant. Okay, so I want the pi over 3 angle in the third quadrant as well. So if I just take pi and add pi over 3 to it, so 4 pi over 3, that would be the angle in the third quadrant where tangent is also equal to square root of 3, okay? Now here the instructions were to give a general formula for the solution. So the idea is you have infinitely many solutions because you can keep going around the circle multiple times. So thinking about this one, so if I take the pi over 3 solution, I can add 2n pi to that to kind of represent going around the circle multiple times. And likewise, I can take 4 pi over 3 and also add 2n pi to that as well. To also represent like all the other angles that you could get if you go around the circle multiple times. Okay. Now here, this is solving for data, but here we have not cotangent of data, but we have cotangent of 2x, okay? So we can kind of think of 2x as being equivalent to data. So that kind of leaves us with 2x could be equal to pi over 3 plus 2n pi, or 4 pi over 3 plus 2n pi. But then I guess we want to solve for x. So that means we'd also have to divide both sides by 2 or multiply both sides by 1/2. So if I do that, that will leave me with x equals pi over 6. Okay. And then dividing by 2 will leave us with plus n pi after that. The 2's would cancel. Likewise here, if you divide everything by 2, that will give you 4 pi over 6 plus n pi. So then this is at least one way that you could write out the solutions to the problem. Yeah, so that's a good point though. So although this answer is correct, there is maybe another way that you could write the solution as well. So thinking of tangent as having a period of pi specifically. So when I was thinking about the angles where tangent of theta is equal to √3, so one solution was pi over 3, and then I was kind of thinking like what other angle from 0 to 2 pi what would also have tangent being equal to square root of 3. So the other angle was in the third quadrant, it was 4 pi over 3. But actually, since tangent has a period of pi, so I kind of realized it after I wrote this down, but I decided to kind of continue with what I had. But in retrospect, I could have gotten the same set of angles just by taking pi over 3 and adding just n pi to that. Since tangent had a period of pi, there was no need to keep going around the circle by 2 pi. Tangent repeats every pi instead, so actually just pi over 3 plus n pi would have worked as well. So instead of doing both of these together is kind of covered by just doing this. Now, yeah, you would still have to solve for x after that, though. So you could also write the solution like this instead. Okay. All right. So pi times k. So I guess maybe you guys tend to use the letter k more often. I guess I was using n, but you could certainly use k as well. So like pi over 3 plus pi k. And then after that, divide by 2 if you want to solve for x. Okay. The red one is correct, but so is the one in black as well. The one in the black is a little bit more complicated, but it's still a correct answer as well, though. Yeah, okay. So here it was a matter of for tangent and cotangent specifically, since they have a period of pi, there was no need for me to find the two angles in the from the 0 to 2 pi, and then add 2n pi to that. So this is okay, what I did here, but it's not necessary for tangent or cotangent, because you can express these two solutions in one line by just doing this. Yeah, so this line here is equivalent to both of these two together, if you will. Okay? So maybe I'll write it like this. Okay. So the red is kind of like a sort of simplified solution, but the black is also good. And the black one, or what I did in black, I guess, is what you'd have to do for actually the other trig functions. But tangent and cotangent specifically, having a period of only pi, you can actually kind of simplify that a little bit. So I was maybe just doing this because I was thinking of like how all the other trig functions work. Okay. So this is okay, but you can also do what we did in red as well, and that would maybe look a little bit easier, but both should still be correct. So could you include 4 pi over 3 as well? And then is in the interval cotangent minus pi over 2 to pi over 2. Let me see. So cotangent, when you say the interval is minus pi over 2 to pi over 2, yeah, I think you're maybe thinking about the arc cotangent, which I believe does have the range from minus pi over 2 to pi over 2. And then I think you have to remove 0 from the middle, I think, because it's a cosine over sine. So yeah, I think you'd have to remove 0 for that one as well. So you're thinking about the arc cotangent there. Now here I included the 4 pi over 3 when I was doing like the black solution, I guess. But the black solution is actually like these two together can be combined into this one single equation in red. So you could either do these two separately, or you could do this one thing in red as well, and they would both give you the right answer in the end. It's just a matter of writing the answer a little bit differently for each of them, okay? Okay, all right. So let me see. So I was thinking of also doing D as well, at least. So let's take a look at part D. Okay. Now let's see here. Okay, so this one is a little bit more complicated to start with because here we have an equation that involves like two different trig functions. So it involves both sine and cosine. So when you have an equation like this, it's usually better to try to rewrite your equation so that there's only one trig function in it rather than two. So what I'm going to do first with this equation is I'm going to use the Pythagorean identity that sine squared of x plus cosine squared of x is equal to 1. Or equivalently, we can say that sine squared of x is 1 minus cosine squared of x. And I'm going to use this identity in particular to replace the sine squared in the equation. I'm going to replace it with 1 minus cosine squared. And the thought process for doing that is now this equation is like solely in terms be a little bit easier to work with since it only involves cosine rather than involving both sine and cosine. Okay. All right. So now at this point, I'm going to do just a little bit of simplification. I'm going to maybe distribute the 2 first. So it'll be 2 minus 2 cosine squared of x plus cosine of x, and then equals 1. Okay. All right, and I'm going to rearrange this equation just a little bit more. But right now, when I look at this equation, I kind of notice it's kind of like a quadratic equation. So for a quadratic equation, you want to move everything over to one side of the equation. So you have like everything set equal to 0. So what I'm going to do is I'm going to move, I think I'm going to move these terms over to this side. Okay. So when I move this term over, it's going to become positive 2 cosine squared. When I move this term over, it's going to become minus cosine x. And then when I move the 2 over, it's going to become minus 2. So you'll have 1 minus 2 is negative 1. And then since I moved all of this over to the other side, that will leave me with 0. Okay. So I moved everything over to get it all equal to 0. Okay. And my reasoning for doing that is because I was thinking of this as a quadratic equation.
Wait, I have a
Yes,
question. It's
yeah,
supposed to be minus 2 cos pi x, not 2 cos square x, because the negative in front you cannot just move it around like that. You have to keep the negative in front, and then the rest become plus 2 cos square x plus cos x and plus 1 after you switch it around.
Let me see here. So what I was doing was I was thinking of like adding 2 cosine squared to both sides. And then I was thinking of subtracting cosine x from both sides. Yeah, and then I was gonna also minus 2 from both sides. It's kind of what I was thinking. So then that left me with 0. And I did sort of switch the order after that. So I moved the 0 to the right side actually. And then this stuff I actually just rewrote it but on the left because I thought that would look nicer. But yeah, so that's how I got like a positive 2 cosine squared minus cosine. And then the 1 minus the 2 gave us the negative 1. Okay. All right, is that good?
Yes, it makes sense now. Oh, I do the
Okay.
other way. Yes.
Yeah, great. Okay. So then let me see here. So then, yeah, so we have a quadratic equation. Now this next part, you don't have to do it, but I think some people will find it useful to do this. I'm just gonna kind of, if we think of cosine of x as being like a single variable, which I'm gonna call u for the moment, this equation could be written as a 2u squared minus u minus 1 equals 0. So you don't have to rewrite it in terms of like a new variable u like that. But I think for some people that might look better if you do so. So then for a quadratic equation like this, what you want to do is you want to either factor it or maybe like use the quadratic formula if you're not able to factor it. But you want to try to maybe factor or quadratic formula to solve for u. In this case, I believe it does factor as 2u plus 1 then times u minus 1, okay? So that's going to leave us with kind of two solutions. We have u, either 2u plus 1 is 0, or u minus 1 is 0. So you get either u equals 1, or solving for u over here, you'll get u as negative 1/2 from that, okay? Okay, but we're not quite done yet. So if you remember that u was cosine of x, then that leaves us with cosine of x is negative 1/2. Or cosine of x equals 1. Okay. So now we need to think about what angles x is cosine going to be negative 1/2. And likewise, like what angles x will cosine of x be equal to 1. I'll start with this one because I think this one's a little bit easier. So we know cosine is 1 at an angle of 0. And that's the only angle, I guess, like from 0 to 2 pi, that's equal to 1, aside from 2 pi as well. So if I take 0 and then I add 2n pi to that, to correspond to going around the circle multiple times. So that's like kind of one set of solutions for this equation in particular. But then we also need to solve this equation, cosine of x equals negative 1/2. So let me think about that. So cosine is 1/2 at the pi over 3 angle. But for cosine to be negative, it has to be in the second and the third quadrant. So it's pi over 3 angle, but in the second and third quadrant. So I think that would be 2 pi over 3 and 4 pi over 3. Okay. And then again, I'm going to add 2n pi as well to correspond to going around the circle multiple times. So that kind of leaves us with kind of 3 expressions for the general solution. So x could be 2 pi over 3 plus 2n pi, or it could be 4 pi over 3 plus 2n pi, or it could also be 0 plus 2n pi, which we can just write as 2n pi, okay? So that would be kind of the full set of solutions to our equation. All right. Okay, so any questions about that? Am I gonna do extra questions in the YouTube video? Probably not. So probably whatever questions I ended up doing for this review is probably the only questions that will be on the video. It would just take me too long, I think, to work through, all the other questions. So I think I probably will stop once we finish with this review. And I know we're a little bit over, but I can still do a couple more questions.
I have a question.
Yeah. Yes.
How did you get the 4 pi over 3 plus 2n pi?
Sure. So I guess the way that I'm kind of thinking about this is, well, so I want to think about when is cosine equal to negative 1/2? So I know that cosine is 1/2 at pi over 3. So I'm looking for like the pi over 3 angles, but for cosine to be negative, I specifically want the pi over 3 angle, but like in the second and the third quadrant instead. So what I was thinking is if I take pi and if I like subtract and add pi over 3, that should give me the angles that I'm looking for in the second and the third quadrant. So I did like pi minus pi over 3 to get the 2 pi over 3. And I also did pi plus pi over 3 to get the 4 pi over 3. And the reason why I picked these two in particular is because I was just thinking about finding the solutions between 0 and 2 pi first. Because once you get all the solutions in this interval, to get all the other solutions, you would add 2n pi to correspond to going around the circle more than once, okay?
Got it.
All right, great. Okay, so there's one more part that I never quite went over for the review, which is just proving some trig identities. So I kind of had like 4 examples here. We can maybe do 2 of them to round out the review. So looking at these 4 choices, do you guys maybe want to pick 2 of them for me to work through? I think I'll pick the first 2 that I see either posted in the chat or the first 2 that were mentioned through voice.
D.
We'll do, all right, B and D, got it. All right, let's see. So we're going to do B and D. So I think that I do have the solutions, or at least not the solutions, but the answers to each of these questions as well. So if I can find the answers, then I can also at least include the answers to all the problems in the YouTube video. So maybe if you want to like practice some of these questions and then check if your answer was correct, you can do that. Aside from that, you can also visit us in our tutoring lab if you wanted to work through some more of these questions. And I or some of our tutors could try to help you out with the questions that we weren't able to get to, okay?
I have one more thing to say.
Yeah, sure.
So the last review, the YouTube video was fine, but the resolution was very like bad. Is there a way like you could upload this documents of what you're working? So
yeah, I'm hoping to do that, and I'm also hoping the video for this one will be better as well. So the first review, I was doing it at home with my laptop, and I think that wasn't working so well. I'm actually on campus right now for this review, and I'm using our very fancy and expensive equipment for it, so I'm hoping it will turn out better, okay?
All right, thanks.
Okay, great. Yeah, because I knew the first review, it just wasn't quite to my liking so much, so I decided I should be on campus for the future reviews. Okay. So let's round out today with these last two problems, proving these identities. So I'll start with B first. And for these problems, it's kind of hard, but you kind of just want to just kind of apply like whatever identities come to your mind and, you know, hope that everything works out, I want to say. So I guess like for this problem, you know, what I tend to do is I start with one side of the identity. Here I'm going to start with the left side. Because I'm thinking that there's something that I kind of immediately see that we might be able to do on the left, which is using the Pythagorean identity. So we know that sine squared plus cosine squared is 1. So I'm kind of thinking we can maybe try doing sine squared as 1 minus cosine squared. Okay. So that's what I'm going to do first. I'm going to rewrite sine squared as 1 minus cosine squared. Yeah, that's right. Okay. So there's maybe I see a couple things we could do here. Yeah, okay. So yeah, someone said that you can cancel with the bottom. So to see exactly how it can cancel with the bottom, in the numerator, we can factor what we have right now. Okay. So in the numerator, what we have is a difference of squares. Okay. So you can kind of think of it as like 1, you can think of it as 1 squared, and then minus cosine squared. So whenever we have a difference of squares like this, you can always factor a difference of squares. So I know like whenever you have a squared minus b squared, you can factor it as like a plus b times a minus b. Yeah, that's right. So 1 minus cosine squared, we can factor it as like 1 plus cosine, and then times 1 minus cosine. So then that works out nicely because the 1 minus cosines will now cancel from numerator and denominator, okay? So that'll leave you with like that final answer of 1 plus cosine of x, which is what we wanted on the right-hand side, okay? Great. And then we'll just look at D and we'll end the review with that, okay? So in D, looking at this, I think, right, okay. So I don't really see much else to do, but to maybe try to rewrite things in terms of cosines and sines. So cotangent we'll say is, let's see here, cotangent is cosine over sine. Okay. And then tangent is sine over cosine. Okay. Now from here, I think what we should do is get a common denominator and put it all into a single fraction. And I guess partly that will be useful because it will at least get rid of, like right now we have 2 terms being added, but in the end we don't want to have 2 terms being added. So we should try to combine these, I think, by getting a common denominator. So I guess we should multiply this one top and bottom by cosine. Then we should multiply this one top and bottom by sine. Okay. So that will leave us with cosine squared x over sine times cosine. And then we're going to get plus, and then here we're going to have sine squared over the common denominator. All right. So then cosine squared plus sine squared, that's the Pythagorean identity. So we know that's all equal to 1. Okay. And then lastly, yeah, to see, looking at what the final expression looks like, we're knowing that 1 over, so let's write this as 1 over sine times 1 over cosine. And then, yeah, we know that 1 over sine is cosecant, and 1 over cosine is secant. Okay. And then, of course, multiplication is commutative, so you can always switch the order like that. Okay. All right, cool. Yeah, all right, good. So I guess that pretty much wraps up the review then. So I went a little bit over, but I guess that's okay. Any kind of like last questions before we wrap things up?
In our class review, there's a graph, and it says like just from like looking at the graph, can you write the equation and the everything? So basically, the question was using the graph below, write a cosine function, modeling the point shown, and write the phase shift as small as possible in either direction.
Okay.
So how would you solve something like if there's like a graph given and then you have to like find the equation?
Sure, okay. So let me see here. Let me...
Can I upload photos into the chat?
You can. I might be able to pull that review up as well real quick. Let me see if I can. I don't quite see it, so that doesn't work. Okay.
Okay, yeah, I just uploaded it.
Okay, great. So let me go ahead and pull it up. Oh yeah, sure. So if you want to stop by our tutoring lab, I can give that information real quick. So we're located in the basement of the library. The room number, if I'm not mistaken, is 1401. But this is the very big room at the center of the basement of the library. So if you like go down the stairs, you'll see it immediately. You'll enter through, we have like a sort of a double door entrance. So when you see like the double doors, that's where you enter through. Okay. And we have like someone at the front desk who can kind of help you, like kind of explain how things work if it's your first time. Okay. And then this is it's a drop-in tutoring, so you don't have to make an appointment or anything. And it's funded through your tuition so that you don't have to like pay anything either, at least any more than you've already done through your tuition. Okay. All right, now let me see here. And then I'm going to go ahead and pull up this file. Okay. So let me grab this real quick. Okay. Give me a couple seconds. Okay, I'm going to go ahead and reshare my OneNote real quick now. All right. Okay. So use the graph below to write it as a cosine function. Okay. And write the phase shift as small as possible in the direction as well. Okay, okay. Okay, I see. Okay. So I guess maybe the first thing that comes to my mind is I guess like as a cosine function, we could maybe try to write it in this kind of form. Looking at the graph, I can kind of see that there's no vertical shift, and I can kind of identify the amplitude as being 5. Okay. Now I kind of see there's no vertical shift because it's already symmetric, like about the x-axis. So if it weren't symmetric, then I would kind of know it was shifted somehow vertically. Okay. But yeah, so there's no vertical shift, and I see the amplitude is 5. That's kind of the first thing that I'll note. Let's try to figure out the period next, because knowing the period will tell us what B should be. So to get the period, you can look for where, for the distance between like 2 of the high points, or maybe between like 2 of the low points, for instance. So if I look at the distance maybe between these 2 low points, so we go from negative 2 pi for the first low point, all the way to 4 pi. So that's like a 1 full period from negative 2 pi to 4 pi. So the total length of this period is 2 pi plus 4 pi for a total of 6 pi. Okay. Now, because the period is supposed to be equal to 2 pi over b, okay, I guess what I want to do then is I want to solve for b. So I'm going to multiply the b over to this side. And then I'm going to divide the 6 pi over to the other side as well. So b is 2 pi over 6 pi, which you can simplify to be 1 over 3. Okay. All right, so then let me see here. We have this function right now. It's the amplitude was 5. The b was 1/3. Okay. Now let's see here. In order to, now I guess like there's like a horizontal shift as well, right? So, but thinking about it, I think I'm going to write it like this instead, in this kind of form. because if I write it as 1/3 and then parentheses x plus or minus something, this number that I write down will correspond to the horizontal shift. So it's a little bit easier for me, I think, to write it in this fashion instead of in this fashion, okay? Okay, so then let's think about how much this graph has maybe been shifted. So to do that, we need to know what the ordinary cosine function looks like. So I know the ordinary cosine function, its amplitude is 1, but maybe to make it look nicer, I'll draw it up here instead. But I know that cosine starts at the high point when theta is 0. And then it goes down and up after that. So I know that cosine starts at a high point when theta is 0, but it looks like that high point has been shifted over some amount. So we could either shift it to the right by a total of pi, or we could shift it also to the left all the way to here. That would be a total of shifting it to the left 5 pi units altogether. So we could do we could do a x minus pi here to say that we're shifting to the right pi units. Or we could do x plus 5 pi to shift it to the left 5 pi units, okay? But this one says to use the smallest shift in either direction. So that would correspond to the shifting to the right by pi units, okay? So then this would be a formula for the graph of this function as a cosine function. I don't think it's too important, but you could distribute the 1/3 to get 1/3 x minus pi over 3 if you wanted it in a bx minus c type of form. And I forgot that you guys tend to write as bx minus c, right? Okay. All right, so then that will kind of just be an example for this problem, how we would have done it, okay?
Why did you multiply the 1/3 to the pi? I thought the x was just only part of the bx.
Sure. So remember that when you have it in this form, like bx minus c. Well, so I guess first, I don't think it was too important to multiply the 1/3 over, but I think you could have left it in this form as well. But remember that when you write it in this form, remember that the phase shift, well, I guess we could have done it in this as well. Maybe just would have taken a little bit more work. So the phase shift is c over b, right? So perhaps we could have done it like this as well. So let's say I set up my equation to look like this right now. So the last thing to do is to figure out what the c should be equal to. So I guess maybe once we figured out the shift was to the right by pi units, we could have said up here that the phase shift was pi. We figured out earlier that b was 1/3. And then if you multiply the 1/3 over to the other side, you get 1/3 pi. So I guess that's another way that you could have done it, set up an equation to solve for c. And then you could plug in pi over 3 for c, and that would have given you the same answer, okay? But the reason why I did it this way is just because I know that whenever you have something let me see what these are. Okay, yeah, okay. Yeah, so it's just the idea that whenever you have a horizontal shift, horizontal shifts come from adding or subtracting some amount to x. So I wanted to, I guess write it in the form where we had x plus or minus something. and the shift being pi to the right, so that's why you want to subtract pi from the x. But to do it correctly, it's subtracting only on the x to get the shift, and then you have to distribute the 1/3 to get the c, if you will. Okay. Okay. All right, cool. So then I guess let's go ahead and wrap things up with that, okay? So I will try to get the recording up later tonight. And then I'll try to email everyone either tonight, or I might have to wait until tomorrow morning as well, depending on how late it becomes, okay?